In today's lesson, we're going to model inverse and joint variation. So inverse variation is directly, well, in a sense, related to direct variation, which we did a long time ago. And inverse variation can be represented as y equals a over x. Remember, a is our constant of variation, which also can be used as the variable k. But inverse variation can also be rewritten as xy equals a. We see it written either way as y over a over x or xy equals a. So in this first example, we want to determine whether x and y show direct variation, inverse variation, or neither. So in this first one, it doesn't really look like much, but if I rewrite this as y equals 3x, I can see that it follows the pattern of y equals ax, which you may remember is direct variation. It goes through the origin, it's linear, so a is direct variation. And the next one, for B, if we look at this one, it matches exactly what we just saw for inverse variation, except here we have x instead of y. We could multiply y on both sides, and then we have xy equals 3, which I expressed as also direct variation, or xy, and then I could divide by x, and then I'd have y equals 3 over x. In either case, this is definitely inverse variation. And this last one I have x plus y. Well, there's really nothing I can do with it. I'm just saying x plus y. There's no multiplication, division that I can do. In this case, this is neither of those. In my next example, we have variables x and y vary inversely, so we're told that. We want to write an equation that relates x and y, given that x equals 1/3 and y equals 15. So let's go ahead and use the one y equals a over x, and we just substitute in what we know. So 15 equals a over x, which is 1/3. If we substitute it in here, so we need to figure out what our constant of variation is. So I would just take both sides and multiply by 3. So thus we would be given 45 as our a. So a equals 45. And now all I would need to do is write my final equation. So it would just simply be y equals 45 over x. And if I wanted to find values of y or x, I could substitute those in, and I can find other values that work with this equation. So we can check for inverse variation if we're given a set of data. If we write it as x times y, it should equal our constant of variation or come close to it. If we're dealing with real-world data, it may not be exactly the same number, but it'd be fairly close. So we can. But if this is the case, then we know we have inverse variation in our hand. So let's look at an example. So for instance, if we're talking about computer chips here, and they're made from these silicon wafers. Silicon is just a form of sand. We can write a model that gives C is a function of A, where C is the number of chips and A is the area of the silicon wafer. And so I'm given some data where we have, the area is 58 millimeters squared. We can make, 448, and if that's A is 62, then this is 424. So I'm sorry, I said the silicon wafer. So basically, it's the area of the chip. So the larger the area of the chip that we cut out of the silicon wafer, the less chips we get. It's kind of like if you have some cookie dough, the bigger the cookies, the few cookies you're going to have if given a certain amount of dough. So we're going to calculate this product. We're just going to multiply A with C. This would be like our X and Y. And if we look at these values, so we multiply 58 with 448, and we get 25,984. And then the next ordered pair, we get 62, 288, and so forth and so on. And they're all hovering around the same number. It's all approximately 2,600. So it looks like we could estimate our A, lowercase a, our constant of variation, as being 2,600. So thus, our equation we could write as A times C, which is 26,000, and then C is equal to 26,000 over A. So it's all, a little bit relative since we're dealing with real world data. And of course, if I want to make a prediction, if I want to say that the area of the chip is 81 millimeters squared, I would just substitute that in, and that would give me approximately 321 using that equation that we derived. The next thing I want to talk about is joint variation. So this happens when you have a product of two or more quantities. So let's say I have Z varies jointly with X and Y. So Z would vary jointly with these two, but please take note, we still have our constant of variation of A. So, and this one, P, varies jointly with Q, R, and S, but again, we still have our constant of variation A. So this one looks like kind of like joint variation since we're multiplying these, but here we're multiplying two or three or more items together. So joint variation, you have several quantities that are varying with something else. So in this example, it says Z varies jointly with X and Y. So given Z is equal to 60, when X equals -4 and Y equals 5, we want to find what our constant of variation is given that. So let me write out that Z varies jointly with X and Y. So we have two variables that Z varies directly with. Could be 3, could be more. And I'm going to substitute what I know. So Z is 60. Is our constant of variation, which we need to find. And then times -4 times 5. So 60 would equal to, this gives us -20A. And then I divide by -20, which will give me -3. So my constant of variation is -3. So therefore, my equation is Z is equal to -3XY. And then if given values for X and Y, I can find what Z is, or Z and X, or Z and Y. Then it's just a piece of cake. The last thing is being able to just write an equation, just given a relationship, given a verbal description. Can you come up with what the equation is? So let's say I start off with Y varies inversely with X. Okay, so that's pretty direct. We've already discussed what that is. So it's simply going to be Y is equal to A over X. But how to write that. I could switch it up. I could say X varies inversely with Y, and then we would switch the X and Y. So the wording can be, you just kind of learn what the wording means here. Here Z varies jointly with X, Y, and R. So 3 variables that z varies directly with, so it would look like this. Z is equal to a, x, y, and r. But what about y varies inversely with the square of x? So not just with x, but with the square of x. So it'll look like this. And one thing I want you to kind of notice is that the thing that varies, so y varies, z varies, y varies, that's what's on the by itself on one side of the equal sign, okay, and then everything else is on the other side. So that's another way to kind of think about how to read that. So when I say z varies directly with y and inversely with x, oh, well, z is going to equal to ay, so directly with y, okay, but inversely with x. So y is in the numerator, so if it was just z varies directly with y, it would be z equals ay, and if it was just inversely with x, z would equal a over x. Okay, so this would be direct, this would be inverse, but together it's this. And then finally, x varies jointly with tr and inversely with x. So t and r will be multiplied together, but s will most likely be in the denominator, so it would look like this. So anything that varies inversely will be in the denominator. If it's direct or jointly means you'll multiply it together, but it'll be the numerator, and directly will be in the numerator as well. So anyway, that's how you can read those. Anyway, that's modeling inverse and joint variation.